19.46. A certain system absorbs 0.3 kilojoules of heat and has 0.7 kilojoules of work performed on it. What is the value of delta E for the change? Is the overall change exothermic or endothermic? All right, so if you turn to page 870 in your book, it describes the first law of thermodynamics. And the first law of thermodynamics is delta E is equal to Q plus W. And let's see, Q is describes the absorption or release of heat, and then work is W is the work done on the system. So in this case right here, we have turn to it really quick. This is a straightforward problem, but anyways, so the system absorbs 0.3 kilojoules. So as I said earlier, this is Q is the amount of heat released or absorbed, so you got 0.3 kilojoules. And W is the amount of work done on it, and we had 0.7 kilojoules. So it's just a matter of adding them up, and you end up with just 1 kilojoule. So that would be the answer for that. And then as to whether or not it is endothermic or exothermic, the overall process is endothermic, which means that the internal energy of the system increases. Notice that both terms, Q and W, contribute to the increase in internal energy of the system. The system gains heat, which is delta Q, right here. Just reiterating this. And the work done on it. So we have positive, well, these values are positive, increase in internal energy, therefore endothermic. So, yes, endothermic. There you go.
Okay, this is 19.48. Kind of long, because suppose that you were pumping an automobile tire with a hand pump that pushed 24 square inches of air into the tire on each stroke, and that during one such stroke, the opposing pressure in the tire was 30 pounds per inches squared above the normal atmospheric pressure of 14.7 pounds per inches squared. Calculate the number of joules of work accomplished during each stroke. And then it tells us that 1 liter ATM is 101.325 joules. So this is actually a really straightforward problem, just disguised as a hard problem, because they give us everything in inches and inches squared and inches cubed, which is ridiculous because who does anything in inches nowadays, but apparently they do. What we're going to use is an equation, which I'm trying to find which page it's on for you in the book. Should be towards the beginning of the chapter. Which one am I looking for? Well, anyways, it's at the very beginning of the chapter. It's involving the first law of thermodynamics, where work, okay, new marker. Work is equal to pressure times change in volume. It's at the very beginning of the chapter, and you can find it in your book. So that means we need to find the total pressure and find the change in volume. But what they do is they give us this conversion factor of 1 liter ATM being equal to 101.325 joules. So that means that we need to get them into liters and ATMs, basically, so that we can use that. So what we're going to do first is find our total pressure. So our total pressure is going to be the pressure that we exert with the bike pump plus the atmospheric pressure. So it was 30 per pump, pounds per inches squared, or sorry, cubed. Oh no, that is squared. Pounds per inches squared. And then the atmospheric pressure they gave us was 14.7 pounds per inches squared. So our total pressure is going to be 44.7 pounds per inches squared. So that's going to be our pressure. But first we need to get it into ATMs. So we have 44.7 inches squared, and they already told us that this was the atmospheric pressure, so that's going to be 1 atmosphere. So we just use that again as our conversion factor. Why don't I need to work? There we go, good marker. Okay, so then we're going to do 1 ATM is equal to 14.7 pounds per inches squared. So we're just using this because they told us that this was the atmospheric pressure. So those cross out. Now we have our pressure in atmospheres, and that comes out to 3.04 atm. That's our final pressure, P. So now we need to get our change in volume. So they told us that it was 24 inches cubed. I'm going to come back over here on our volume. 24 inches cubed. We're going to use our inches to centimeters conversion. Those conversions and stuff are all in the book too, in your appendixes. I think they're in the front and the back actually. So it's going to be 2.54 centimeters per inches cubed. And since it's the inches are cubed here, you cube, or just remember in dimensional analysis, you cube the whole thing because you need it all to be cubed. So that's including the number. Then you're just going to times that by 1 liter is going to be 1,000 centimeters cubed. Remember this because 1 centimeter cubed is what a milliliter is. And if you bring that all through, our change in volume ends up being 0.393 liters. So now we have both our change in volume and our pressure. So we're going to plug them in here to our problem. So our work is equal to 3.04 atm times 0.393 liters. And that gives us 1.19 liters ATMs, which is what they gave us the conversion factor for up here. So if we go ahead and just times by that 101.325 joules, it's equal to 1 liter ATM. And then our liters ATMs cancels out, and we end up with 121 joules as our answer. Did I just write a backwards J? Joules. So that's how it's done. It's really just a plug and chug, but it was just a matter of getting the right units.
1950, calculate the change in enthalpy and the change in internal energy for the following reactions at 25 degrees Celsius. If necessary, refer to the data table in C.2 in Appendix C. So we'll just run through these equations. First thing that we're going to do is we're going to find the enthalpy for everything. So let's do that. These reactions. So this is the reaction that they gave us. And then the change in enthalpy, this degree right here just signifies that it took place at standard reaction, takes place at a certain temperature. So anyway, so heat of formation, and this is just delta, this is going to, it's final minus initial, so we're taking the change in enthalpy of the products minus the change in enthalpy of the reactants. So we got PB solid plus this right here is just a marker for the change in, we have 3 moles of H2O, so we're going to need to make note of that by just putting it through right there. All that minus, this is the reactants. Alright, so that just kind of sets up the stage, change in enthalpy per mole for each of these. And so these values right here can be found in, like they said, Appendix C.2. So you'll want to look, that would be the next step, is you're going to look up each of these values. And heat of enthalpy for each mole. So, so it's important that we use the coefficients to carry down. So anyway, so now it's just plugging in the values. This is super tedious, but it's fun. Mole times 0 kilojoules per mole plus 1 mole times 0 kilojoules per mole plus 3 moles. This one gets exciting. Times negative 241.8. Again, you can find that in the appendix. Just look it up for H2O in a gas state. Minus Alright, so plugging in these values, 3 times 0, 1 times 0, all of that minus by this right here. This is our reactants. These are our products. Delta H ends up being positive 221.8 24.58 kilojoules. And so from that, we're going to use that to find the internal energy, the change in internal energy, which is delta E. And we're going to use this equation. You can find this in your book. But delta E is equal to delta H minus nRT. So delta H, 24.58 kilojoules minus N stands for the number of moles in gas, the change in number of moles of gas. So 2 moles. Ours is standard, which is 8.314 joules per mole times Kelvin. So to convert that, we have kilojoules. This is in joules, so we're going to have to times it by 10 to the -3 to get it into just joules. So times T, temperature. This is standard, so 298 degrees Kelvin. And when you work all of that out, you end up with 19.6 kilojoules. So actually, that just kind of sets the stage for the rest of them. If you can understand this one, then you can understand the rest. So first things first is finding the change in enthalpy, delta H. You just use this equation. You did this in like chapter 7 during the first semester. You can check in your book if you have more questions or come to us. The values there found in appendix C. Plug them in, do the algebra, work out delta H. And then you're going to use this equation also in your book to find change in internal energy. And so just number of moles times R times temperature, and RT, those are constant. So anyways, that shows you the guideline, and then you can do the rest and check your answers in the back of the book.
Okay, this is 19.52. It says the reaction shown here has a delta H of negative 163.14 kilojoules. What is the value of delta E for the decomposition of 186 grams of N2O at 25 degrees Celsius? If we assume that delta H doesn't change appreciably with temperature, what is delta E for the same reaction at 217 degrees Celsius? So this is just kind of the same thing we've been doing, and it's kind of just 2 problems in one as well. We're going to use the equation, which you can find in your book, that is delta E equals delta H minus nRT. We write delta A because it's change in moles of gas. So we're basically just going to plug everything in. Our delta H that they give us is at negative, negative 163.14 kilojoules for this problem. And then we can see that our change in moles of gas over here, we have 2 and 1, so 3 moles of gas. And over here we only have 2. So our change in moles of gas is just going to be 1. And R is a constant, which you should have memorized at some point. 8.314. It's kind of easy because this is like pi to me. I don't have to remember it. Joules per moles Kelvin. And then they told us that temperature was 25 degrees Celsius for the first part, which we just need to go ahead and change to kelvins by adding 3 to it. We get 298 kelvins. So that's for the first first little bit, we just need to plug everything in. So, yeah, first we just need to plug everything in here. So we're gonna have 163.4 kilojoules minus, this is just 1 mole, change R is 8.314, which we need to convert into kilojoules. Since everything else we're dealing with is in kilojoules, it's just easier to convert that one thing and convert everything else. So it's just going to be 0.008314 kilojoules per moles Kelvin, and then times by 298 Kelvin. And this is an easy way to check yourself to make sure on problems like this is that you're using everything right. Is your units end up canceling out. Kelvins cancel with kelvins, moles cancel with moles. You end up in kilojoules all around. So the answer that you get if you plug that in the calculator is negative 165.62 kilojoules. So that's how many kilojoules in 1 mole. So we need to figure out the kilojoules in 180. Well, we need to figure out, yeah, the kilojoules in 100 and the amount that we have here going on. And what they told us was that we had 186 grams of N2O. So 186 grams of N2O. And we're just going to have to use good old dimensional analysis to multiply to get the moles. So from the periodic table, it's 44.02 grams of N2O for 1 mole. And that gives us 4.23 moles of N2O, which we can then multiply with this. Since this is the change in enthalpy for this equation, we know that it's we can use it as a merge factor because we know that this is the change in enthalpy for 2 moles of N2O because it's changed for this equation specific right here, and that has 2 moles of N2O in it. So that's already so that's the only tricky part to that. You just have to make sure you use the coefficient of what you're using here. So and then we get negative 350 point, well, that's negative 350 kilojoules. So that's our answer for the first part when they're asking about 25 degrees Celsius. Now we just need to do the exact same thing as what we just did, but for our 217 degrees Celsius. So we're going to plug everything in again. It's negative 163. I'm not going to plug everything in again. It's this. It's still 1 mole. It's still this constant, but now instead of 298, it's 490. And that comes out to be negative, can't forget the negatives here, and negative 167.21 kilojoules. So then if we just go over here, and it's going to be the same thing, 4.23 moles is still how much we're dealing with. We're just at a higher temperature now, and it's going to be 167.21 here instead. Kilojoules, and over 2 moles, you just multiply that out, and it's negative 353. Oh no, if you round it, it's 354. Sorry. So
fix that. 19.54, use the table 7.2 to calculate delta H for the following reactions. On the basis of their values of delta H, which are favored to occur spontaneously. All right, so we've got this first reaction over here. Let's see, yes. So we want to calculate delta H. We kind of did this and over it earlier, but just go through it again. Information per mole, CaCO3, solid. These values found in Appendix C of your textbook. Delta H right here indicates, delta products minus reactants. So change in enthalpy for the products over the change in enthalpy of the products minus the enthalpy of the reactants. You know what I'm saying. CO2, gas, plus delta H. All right, so find these values in your book, but we have 1 mole. So it's going to be 1 mole times -1207 kilojoules per mole. Minus 1. This should really be minus 1. Alright, awesome. So once you have that out, you're just going to do some basic algebra, and you'll just get -178 kilojoules, which is sweet. So what they want us to do is they want us to determine from the change in enthalpy whether or not the reaction is spontaneous or non-spontaneous. Is the reaction likely to occur or not? And so for that, what we're going to do is we're going to want to use Gibbs free energy. This equation can be found in your book on page 887, and it's just delta G is equal to delta H minus change in temperature. This is standard, so 298.15 Kelvin. We know we're using that because there's the degree right here, so standard temperature times delta S. All right, so that is what you're going to use to determine it, whether or not this reaction is favorable or not. The key here is looking at, okay, so we just found our delta H. And because our value here is negative kilojoules, it's going to be favored, so it will occur just spontaneously. And you get that just from this equation right here. If delta G is a positive number, then it is not likely to occur. But if it's a negative number, then it is likely to occur. And anyways, we're going just off of this right here, because I said based off the change in enthalpy. So we have a negative enthalpy, so that's going to push us towards a negative Gibbs free. And anyway, so it'll be spontaneous, it'll be favored. So then they're going to have us run through these for 2 other problems. You can find delta H doing, plugging in your values, doing your algebra for part B, and you should get negative 311 kilojoules. Again, this value is negative. So it is classified as being favored or spontaneous. The reaction is likely to occur without any input of energy. Don't know how to spell spontaneous, don't worry. Life is good. Delta H for part C is going to be a positive 1084.3 kilojoules. And judging off of the enthalpy alone, because this value is positive, we'd have if we plugged it into the Gibbs free energy equation, we'd have a positive value, so it would be not spontaneous, not favored. There you go.
Okay, we're looking at 19.56, and this one says, what factors must you consider to determine the sign of delta S for the reaction shown here if it occurs at constant temperature? So, this is the reaction. It's talking about delta S, and it kind of just wants us to look at what we think the sign of delta S is going to be based on the equation. So there's kind of three factors that you need to look at. The first one is the number of moles of products versus the number of moles of reactants. So delta S is talking about spontaneity, and so something is going to have more delta S if there's more particles that come out of it. So here we have 2 moles of reactants, and over here we have 3 moles of products. So that would indicate that delta S is going to be positive. The second factor we want to look at is the state of the products versus reactants. So something in the solid state is a lot more orderly. I mean, imagine that as a solid. It's a lot more orderly than, say, like this is a liquid, and then that's a gas. So gases are a lot more spontaneous. So if you have more, so here we have gases and here we have gases, but so we're not like getting less spontaneous or more spontaneous. That one doesn't really indicate anything, except for we do have more moles of gas on that side than on this side. So so that does indicate positive. Then number 3 is the complexity of the molecules. So N2O is a more complex molecule than N2 or O2. And more complex molecules breaking up into less complex molecules is going to indicate a positive X. So all 3 of our factors in this case kind of indicate a positive X, so it would be safe to assume that S in this case would be positive.
18.58 or 19.58. Yes. Predict the algebraic sign of entropy change for the following reactions. All right, entropy, yes. Jacqueline talked about this in the previous equation. Dealing with delta S, that is what we are talking about. Delta S. Spontaneity. Yeah, it's great stuff. All right. Predict the algebraic sign. So, straightforward problem here. Delta S, yes. The key to these problems is going to be looking at the number of moles. Simple rule. Basically, if the number of moles of gas increases, then delta S is going to be positive. It's like Jacqueline explained, gas, yeah, this is more orderly. We got our solid, we got our liquid, and we got our gas, which is all over the place. Anyway, so, yeah, anyways, so key to these problems, number of moles. Number of moles increase, number of moles of gas increase, more spontaneity. Anyways, this is really simple. I don't know why I'm keep talking. Anyways, from here we see 1 mole of gas, 1 mole of gas, 1 mole of gas. The change in number of moles of gas is what we want. So change in number of moles of gas. Yes. So for our products, we have 1, and then we've got 2 moles right there, 1, 2. So that's going to give us a negative number. And so that's negative, so the spontaneities, delta S, is also going to be negative. So the answer is B, same thing, number of mole of gaseous materials decrease. Here we have 1 mole of gas on the reactant side. Here we don't have any moles, so it's negative. Yeah, negative. It's going to be less spontaneity is going to be negative delta S. That's all you really need to know. Over here, number 3. Same thing. Oh wow, 1 mole of gas, no moles of gas. So the change is going to be negative. Again, negative delta S, negative entropy. And then here, interesting enough, we have 1 mole of gas on the product side and no moles of gas. So that's going to be a positive number. Positive. We've got a positive gaseous material. It's just appearing. So yeah, so positive delta S, more entropy. It's great. It's fabulous. That's it.
13.60 says calculate the change in entropy for the following reactions in joules per Kelvin from the data in table 19.1. On the basis of their values of change in entropy, which of these reactions are favored to occur spontaneously? So what we're going to do is it's kind of just like calculating delta H for it's exactly like calculating delta H for an equation or a reaction, but you're just going to use the S values. So on the table 19.1, oh, did I write 18? Why do they keep doing that? This is 1960. Okay, so in table 19.1, they give you the S values for separate different compounds. So we're going to do the sum of the S values of the products minus the sum of the S values of the reactants. So our product over here is NH3, so it's going to be, remember to use the coefficient to multiply, so it's going to be 2 times the entropy of NH3 minus, and put that in parentheses, 1 times the entropy of N2 plus 3 times the entropy of H2. So what we need to do then is go to that table, find out what these values are, and plug them in. So this is 2 moles times 192.5 joules per mole Kelvin minus 1 mole times 191.5 joules per mole Kelvin plus 3 moles times 130.6 joules per mole Kelvin. So in the calculator, add those first, then, multiply them. Do this first, then subtract it, just to avoid calculator errors. Your delta S for this is going to be negative 198.3 joules per Kelvin. And because it's negative, that's going to be non-spontaneous. And then just to check your work, the last 2 problems, what we did was we predicted what we thought the sign would be based on the balanced equation. So you can see here that we have 3 plus 1, so 4 moles of gas here turning into 2 moles of gas. So we're decreasing on our moles of gas, decreasing in spontaneity. So we would expect it to be negative and expect it to be non-spontaneous. So that is a good way of checking it. And there are 1, 2, 3, 4, there's like 4 more parts to this, a B, C, D, and E, but they're literally exactly the same as this, but with different values that you can look up in the table. And so I'm not going to write them out, but this is how you do them. And if you need help, you can come see us. All right, 19.62, calculate change in entropy of formation for the following compounds in joules per moles per Kelvin. So the entropy of formation is just going to be, it's just going to be like calculating heat of formation for a product. So the product that they want us in part A, or well, there's 3 of them. So the first one they want is C2H4. So for this, they want entropy of formation. So we're going to make that our product. I'm going to actually move it over here. And that's going to come from carbon and hydrogen, and they're free elements. So carbon, which is a solid by itself, and hydrogen, which we know is a diatomic molecule, so it's going to be H2, and that's a gas. So then we need to balance to make sure that everything's all balanced. We need to put a 2 here and a 2 here so that we have a balanced equation. And now we do exactly what we've been doing. We want, we want here, the delta S of formation of this. So this is the reaction that shows the formation of this. So we just need the delta S for this reaction now. I'm not going to write out that big long thing. You should know that it's going to be the products minus the reactants. So that's going to be 1 mole, that, and again, reference back to table 19.1 to get your values for these things. And if not table 19.1, there's a bigger table in the appendix in the back of the book, so you can also look up that. So 1 mole times 219.8 joules, moles kelvins, and then minus our reactants, which are going to be 2 moles times 5.69 joules per mole Kelvin plus 2 moles times 130.6 joules moles Kelvin. So you get that all in the calculator, and we get our delta S for this equaling negative 52.8 joules per moles Kelvin. So the only difference for this one is that they only give you this to start off with, and you need to figure out the reaction. So, and the other ones, I'll show you how to get the reaction, but this is what we just did in the last problem and the problem before that, and exactly what you do for heat of formation. And so you have plenty of places to go to figure out how to do that, so I'm going to hold off on that. But so the other product they give us is calcium. Sulfate, and it's a hydrate, so it has water. So our pure substances from that are going to be calcium, which is a metal, so it's a solid. Sulfur, which from the periodic table we see is also a solid. O2, diatomic molecules, so we have to make sure we put the 2 there. It's a gas. and H2, which we also have to make sure to put the 2, which is a gas. And then we need to balance it. So to do that, we need to put a 3 here and a 2 here. And then I'll just write the answer that you end up with. You end up with delta S negative 755.5 joules per moles Kelvin. And then just to show you again how you check that, just so you know you're in the ballpark. Here we have 2 and 3, or 3 and 2 gas, and over here we have no gas. So we expect it to be a solid, and also not even looking at the gases, we have 6 moles of substance, and here we only have like 1. And then you've got the hydrate. So really, I guess even if you counted that as 3, it's still, you're significantly decreasing the number of moles, and the spontaneity, so you would predict it to be negative. For the last product that they give us, it's acetic acid, which is a liquid. And we're just going to break it down into H2, C, and O2. Those are gases. That's a solid. Then we need to balance it. You end up with 2 and 2. And that's the entropy you should get after using the table to figure out for this equation. It should be negative 318 joules per Kelvin moles. And that's that.
19.64, nitrogen dioxide, NO2, an air pollutant, dissolves in rainwater to form a dilute solution of nitric acid. The equation for the reaction is calculate delta S for the reaction in joules per Kelvin. So what we're going to do is we're just going to calculate the standard entropy change, which is a lot like finding the heat of formation, the enthalpy, but same basic idea. Sum of the standard entropy of the products minus the sum of the standard entropy of the reactants. And these values you can find in your book. Just look them up, but we'll just go through and show you the basics. All right, so this should look all very familiar. Some of the products, so I'm not going to write out the products, we'll just go straight into the numbers, so that'll be again, this is the products, HNO, 3, HNO3, NO, NO, 2 moles, there we go, minus and this is our reactants. So exciting. This is chemistry at its best. Right, so there we go. Now we're just plugging in the values that we got from the book. So 2 moles times 155.6. Always helpful to write out your units. Probably just helps you make sure you're doing everything right. Everything cancels out. Minus, so long. Not a lot to say. This is pretty straightforward. Plug in the values up front of the book, times the amount of moles that they have in the equation. Make sure your equations are always balanced, that's always helpful. You do some algebra, you all can do that, and you get delta S equals negative 269.7 joules per kilometer.
Kelvin.
Kelvin. Woo! I'm thinking physics. Something else. Anyways, there you go. That's the answer.
Okay, this is 19.66. It says phosgene, which is COCl2, was used as a war gas during World War I. It reacts with the moisture in the lungs to produce hydrochloric acid, which causes the lungs to fill with fluid, and carbon monoxide, which asphyxiates the victim. Both lead ultimately to death. So that's nice. It gives us the entropy and heat of formation of phosgene. And it says use this information in the data in table 19.1 to calculate delta G of formation for phosgene in kilojoules per mole. So this is going to be kind of a combination of all the other problems we've been doing so far. They want us to get delta G of formation. So that means that we need to set up an equation showing all of the components of it becoming phosgene, which is COCl2. So that means we're going to have carbon, solid, oxygen, which is a gas, and chlorine, which is also a gas. And then we need to balance it, so that's going to bother me. So to balance it, in this case, we have to put a fraction coefficient in front of the oxygen here. And that's okay to do because really, these coefficients don't have to be whole numbers. That just means that you're using half a mole, or that half a mole of oxygen only combined with a full mole of carbon. It's not a big deal. I know we don't usually see fraction coefficients, but it's like saying I have a half a dozen eggs. It's the same thing. I have half a mole of oxygen. And then we're going to use the equation delta G equals delta H minus temperature times delta S. And since we want the delta G of formation, we're going to use the delta H of formation and the delta S of formation as well. So the first thing we need to do, they gave us delta H of formation in the problem, and they gave us the temperature. So we need to find our delta S of formation, basically.
No!
Did it die?
It died!
Okay, we're back. Sorry about the delay. Our camera died in the middle of this problem, but here we are again with our phosgene killer gas, and here's the equation we're using to get our Gibbs free energy. So they gave us this, and they gave us the temperature, so we need to solve for our entropy change, or entropy of formation. So we're just going to use the table in the book. We're going to do the same thing we've been doing for all the other problems. I think it's table, I can't remember. Table in the book. And I'm not going to go and write it all out anymore because refer to the last problem. We've done that about like 3-4 times now. So I'm just going to just jump right to numbers. So we have products minus reactants. So 1 mole of oxygen. products minus, we add up all of the reactions. So we have 1 mole times 5.69 joules per mole Kelvin plus 1/2 mole times 105.0 joules per mole Kelvin. Oh, I hate this marker. Hold on a second. There we go. Plus 1 mole times 223 joules per mole Kelvin. So, just remember to get all these numbers from the table of delta S of formations in the back of the book or in the chapter. When we put all that into the calculator, we end up with change of entropy for this problem being negative 47 joules per mole Kelvin. Now remember in the problem they wanted us to have it in terms of kilojoules, so I'm just going to go ahead and convert that. It's going to be 0.047 kilojoules per mole Kelvin. Now all we have to do is plug this into the equation along with the things they gave us in the problem to get our delta G. So that's going to be negative 223 kilojoules per mole minus 298 Kelvin. Remember they gave us it and they gave us 25 degrees Celsius, so you have to add 273 to get the kelvins. And we're going to plug this in. And if you look there, we have our kelvins crossing out, so we end up in kilojoules per mole for everything. We end up with negative 209 kilojoules per mole for our Gibbs free motion. That's the answer.
19.68. Compute delta G in kilojoules for the following reactions using the data in table 19.2. This is very similar to the other problems we've been doing. And like they said, the data in table 19.2 will be your friend, because that gives you the standard free energies of formation for typical substances. Again, delta G it's just, products minus reactants. So for this first equation, we'll just jump right into it. Here we have delta G H2SO4. It's our product, so we're going to be subtracting in the reactants. So delta G liquid plus delta G SO3 gas. Alright, so as you can see, products minus reactants. Similar idea of what we've been doing this whole time. Now we're going to plug in the numbers that we found in table 19.2. Key again is looking at the coefficients. This one just has 1 and 1 and 1, so straightforward. Then what we get for the answer is
think,
this the wrong problem again?
no, I just think you wrote it down wrong. Hold on.
Back again, guys. Okay, it's very important that you include all your compounds in your reaction. I goofed up. So here we go. Let's do this again. So H2SO4, we've got 1 mole. Times this value, negative 689.9 kilojoules per mole is found in the book, table 19.2. And that does it for our products. That's all we have. Minus 1 mole times negative 237.2 kilojoules per mole plus 1 mole times negative 370 kilojoules per mole. There you go. Simple algebra, just add it all up. And then you'll get negative 802, or 82.3 kilojoules. There you go, that's the answer. For problem B, same thing, it's just getting those numbers from table 19.2 and putting them in the equation. So when you do all the math, you should get a value of negative 8.8 kilojoules. And for problem C, it's going to be delta G is going to equal positive 70.7 kilojoules. So products minus reactants, and get the values from table 19.2, do some algebra, and you'll be good.
Okay, everyone, this is 19.70. It says, given the following, these two equations, calculate delta G for the reaction here. So this is a lot, we did something really similar with delta H in a past chapter, but this time we're dealing with delta G, but it's really the same thing. So we know delta G for these two equations, and what we need to do is manipulate them in such a way that we can add them together to get this equation. So if you're just looking at it, on this side of the equation, we have N2O and 3O2, and over here we have 4NO. And what you have to remember is that these things can cancel each other if they're on opposite sides. So what we're going to do first is flip this one over so that the products and reactants are on the other sides. So we have 2NO2 on this side. So I'm just going to go ahead and erase it like this. So we flipped it over, and then we're also going to double it. So multiply everything by 2. And so that's going to give us 4NO2 on this side, which is what we have over here. So I'm just going to I'm going to start adding them. So over here we have 4NO, but down here we have, well, I'll just add them. So here we have 4NO, and 2 times 2, so 4NO2. And then this side we have 2N2O plus, we're going to add these up, and then this one's double. So it's actually going to be 5O2. And then we have this, so that's 2, or it's double, sorry. So we have 4NO. So then we can go ahead and cancel things that need canceling. So there's 4NO on this side and 4NO on that side, so they get canceled out. We have just stop it. I think I wrote this one. Oh, okay. Sorry everyone, I realized that I had actually written this wrong. In the original there was a 1 here, not a 2. So that was the complication. So here we double it, there's 2, so it's 1 plus 2, there's actually 3 O2s on this side. Now it makes sense. So when we cancel out what we have on both sides of the equation, we end up with this equation right here. I'm just going to go ahead and erase the things that cancel. So we end up with this, which is actually just this, this final equation flipped over. So what we need to remember is that since we doubled this here, we need to double the delta G. And since we flipped it over, we also need to change the sign. So we change the sign to positive, and then we double it, giving us positive 139.40 kilojoules. And then we added those, so we can add these. We end up with negative 0.016 kilojoules for our delta G of this equation right here. And since the equation we wanted was just this one flipped over, we just have to flip the sign. So it's positive 0.16 kilojoules. Okay.
19.72. Gasol is a mixture of gasoline and ethanol, grain, alcohol. Calculate the maximum work that can be obtained at 25 degrees Celsius and 1 atm by burning 1 mole of gasol. This is the given equation. So they're asking for work. And if you refer to page 891 in your book, it gives you a law. It says, the maximum amount of energy produced by a reaction that can be theoretically harnessed as work is equal to delta G. So what they're saying is work is equal to delta G. Woo! That, you know what that means? Delta G, we need to find that. Let's find it. We're going to do it the same way we've been doing this whole time. Delta G is equal to the sum of the delta G of formations of products minus reactants. So here we go. Delta G. We're just going to go straight to the numbers because that's what really matters. So products, 3 moles. This is referring to the H2O right here. Look this number up, negative 228.6 kilojoules per mole. This number, again, table 19.2, that'll help you out, plus 2 moles right here, carbon dioxide, negative 394.4 kilojoules per mole. Yes, those are our products minus our reactants. Our reactants are 3 moles times 0 plus 1 mole times negative 174.8 kilojoules per mole. These are our reactants. Algebra, love the algebra, keep it going, and we get negative 1299.8 kilojoules. That is our delta G. Again, delta G is equal to the work. Boop, boop, boop. Answer.
Okay, this is 19.74. It says chloroform, formerly used as an anesthetic and now believed to be a carcinogen, has a heat of vaporization of 31.4, shown here. And the change from liquid to gas has a change in entropy, shown here, 94.2. At what temperature do we expect chloroform to boil? As in, at what temperature will liquid and vapor be in equilibrium at 1 atmospheric pressure? So, the key to this one is realizing that at equilibrium, delta G is equal to 0. So if we take this equation, delta G equals delta H minus T delta S. And in this case, the delta H is the delta H of vaporization, since we're going from liquid to gas, that's vaporization. So that works. And this is also standard. They told us in the equation that we have one atmospheric pressure. And so they want to know what temperature will this be at. So we realize that at equilibrium, which would be when this is occurring, delta G is equal to 0. So we can go ahead and set this equal to 0. And now that we have it equal to 0, we can solve for our temperature, which is what we're looking for. So when we do that, we get temperature equals delta H over delta S. And those are what they gave us. So we can just plug those in. This one we actually need to change to joules, so it matches the delta S. So it's actually going to be 0.0314 joules for me. That's better. And that one's already in joules, so just got to be careful, make sure everything's in the same units. That's why it's important to do that for mole Kelvin. So this gives us our answer when we plug it into the calculator. Temperature equals 333 Kelvin, which if you want it in Celsius, you have to minus 273, so it's 60 degrees, sorry, 260 degrees. No, 60. Oh, yeah, 60 degrees Celsius or 333 degrees Kelvin. That's that.
All right, this is 19. Whew. I'm not going back. 19.76 isooctane, an important constituent of gasoline, has a boiling point of 99.3 degrees Celsius and a heat of vaporization of 37.7 kilojoules per mole. What is delta S for the vaporization of 1 mole of isooctane? All right, so what we've got here, little Gibbs free energy, delta G. This is at equilibrium, so it's going to be 0 delta H minus T delta S. And thus, delta H is equal to T delta S. And if we assume that both delta H and delta S are independent of temperature, we can rework the equation so that we have delta S is equal to delta H divided by T equilibrium, which is great. So then it's just a matter of low algebra. 7.7 times 10 to the 3 joules per mole, all over 99, 3 plus 203.15 Kelvin, because we're converting it into Kelvin, and we get 101 joules per mole times Kelvin. So this one right here, Gibbs free energy, it's at equilibrium, so it equals 0. Assuming that these are equal to each other, and then they're independent of temperature, delta H and delta S are independent of temperature, so then we can rework the equation where we have this right here. This is what we want to find. And then from there, we're just plugging in the values that they gave us in the book. 37.7 and 99.3, and converting that into degrees Kelvin. And that's how it's done. Easy enough.
Okay, this is 19.78. It says Determine whether the following reaction, shown here, equation unbalanced, will be spontaneous at 25 degrees Celsius. And then, do we expect appreciable amount of products to form? So, the first thing we need to do is balance the equation. So, what you need to look at is that the number of all of the elements. So we have 2 carbons on both sides. I'm going to do hydrogen mass. 2 carbons on both sides. Here we have 1 N, and here we have 2. So we're going to have some changes here. Here we have 3 O's, and here we have 1, 2, 3, 4, 5. So, or no, sorry, 1, 2, 3, 4, 5, 6. 6 O's. And then for our H's, we have 4 plus 1, which is 5, and then 1, 2, 3, 4, 5, 6, 6. So here we have 5. So as you can see from that, all you have to do is add, wow, I'm not going to add on me. Add a 2 right there. And now we have everything balanced the way that it should be for our equation. Yep. All good. Yeah, so now what we need to do is the sum of the products minus the sum of the reactants. So that's going to be what we've been doing this whole chapter, all of the problems previous to this, pretty much. Not the last 2, but the ones all before that. This whole chapter we've been doing similar things where you just look at the table and you do the sum of the delta G formation or delta S or delta H, either way, the sum of the reactants minus the sum of the products. So in the end, I'm not going to show how to do that again. If you don't know how to do that, refer to the last few problems or come in and see us. Either way, our delta G ends up being negative 479.4 kilojoules. And so since the delta G is negative, we know that yes, it is spontaneous.
Woo! Spontaneous! 19.80, calculate the value of the thermodynamic equilibrium constant for the following reactions at 25 degrees Celsius. Equations are unbalanced. Refer to the data in Appendix C. All right, excellent. So what we're going to want to do is, first of all, let's balance our equation. So if we do this, we find that we need 2 moles of POCl, 2 right there. We're going to want 2 PCl over here, and then just 1 more right there. And I think that should, let's see, 2, oxygen 2, Cl2, 6, Cl6. Perfect, excellent, beautiful. That's what we want. All right, our next step. So they're looking for the equilibrium constant, which is delta, which is Kp. That is our equilibrium constant. That's what we want. This equation here is found in your books. So R and T are both constants that they tell us that it takes place at 25 degrees Celsius. We're going to want to convert that into Kelvin so that our units cancel out. R is a constant, and delta G we will solve for using the methods that we have in the past. I won't do out the math for you because I'm sure you can do it by yourself. Delta G of formation, products minus reactants. Straightforward. You're going to get an answer is negative 1.502 times 10 to the 6 joules is what you'll end up getting for that. That's great. So, and we know that that is equal to negative RT ln of Kp. So RT is just 8.314 joules divided by Kelvin. Kelvin per minute. 25 degrees Celsius converted into Kelvin is 298 degrees Kelvin times ln, just going with what we got, Kp. So we're solving for Kp. So if we divide this out over here by our delta G, we're going to end up with ln of Kp is equal to 606, which is therefore, take the log of both sides, log of Kp, log of that. Is equal to 263, and therefore Kp is equal to 10 to the 26 raised to the 263 power. So that's how you do that. Yes. Same process for over here, part B. You're going to want to find your delta G. When you do your delta G, you end up with 1.4 times 10 to the 5th joules. And again, that is equal to negative RT ln of Kp. We're looking for Kp. So we know that that is equal to, just plugging in our constants, 8.314 joules per Kelvin mole. That's our R value. Kelvin is 298. So we had 27 degrees Celsius, and it's ln of Kp. Super. Divide out by those two values over here, and you'll end up with ln of Kp is equal to negative 56.5. And therefore, doing the math, you get Kp to equal 2.90 times 10 to the 25th. To the negative 25th. That's your answer for part B. So just remember the equation on page 902. Find your delta G's for each equation. Make sure your equations are balanced. You'll be good. Plug in our constants, R and K. Divide it out. Solve for ln of Kp. Solve for Kp. There you go. 19.82. The reaction above has Gibbs free energy, delta G, equal to negative 9.67 kilojoules. A 1 liter reaction vessel at 1000 degrees Celsius contains 0.02 mole NO2, 0.04 mole NO, 0.015 mole N2O, and 0.035 mole O2. Is the reaction at equilibrium? If not, which direction will the reaction proceed to reach equilibrium? So in this case, we're going to be comparing the Kp value to the Q, mass action expression. So we're going to be comparing these two values. What we're going to do is we're going to use the Gibbs free energy equation, which is delta G is equal to negative RT ln Kp. And what we're going to do is we're going to solve for Kp, and that's how we'll find our Kp, and then solve for Q using mass action expression. So let's just jump into it. They give us delta G negative 9.67 times 10 to the 3 joules. They give us it in kilojoules. Multiply times 3 to get the equivalent in joules. R is just a constant, 8.314 joules per Kelvin times mole. converting the degrees Celsius, 1,000 degrees Celsius into Kelvin equals 1,273 Kelvin times ln kV. So you're going to divide out by this, divide out by that on both sides, and you'll end up with ln Kp is equal to 0.914. Therefore, the Kp is equal to 2.49. You can use your calculator to figure that out. So that's what our Kp value is. Next, we want to solve for Q. So, again, Q, we just have products over reactants. And they're all 1 mole, so that's good. So, N2O over O2, 1 mole. They all have 1 coefficient. NO2, NO. Products over reactants, raise their coefficients appropriately. And they give us the concentrations, so it's just a matter of plugging it in. So we just have 0.015 times 0.035 all over 0.02 times 0.04. And when we do that, we get 0.66. So now we're looking at, this is our Q value. So now we're going to be comparing those two. And since the value of Q is less than the value of K, the system is not at equilibrium and must shift to the right to reach equilibrium. So that's how it's done. Shifting to the right, so it's going to be shifting to the products. So there'll be more this will be a bigger number divided out. This will shift to equilibrium. Q value will get bigger. Yes.
Alright, 19.84 says a reaction that can convert coal to methane, the chief component of natural gas, is shown there below, for which delta G is negative 50.79 kilojoules per mole. What is the value of Kp for this reaction at 25 degrees Celsius, and does this value of Kp suggest that studying this reaction as a means of methane production is worthwhile pursuing? Alright, so for this problem, we're going to use the equation delta G equals negative RT natural log Kp. They gave us delta G, they gave us temperature, R is a constant, so we just plug everything in and solve for Kp, basically. They gave us delta G was negative 50.79, and I think they gave it to us in kilojoules, so we're going to go ahead and times that by 10 to the negative 3, so we have it in joules. And we have to do that so that we're in the same units as the R constant value, negative. So R is 8.314 joules per Kelvin mole. They also gave us temperature in Celsius, which we need to convert to Kelvin so that we're in the same units. So 25 plus 273 is going to be 298 Kelvin. And that's natural log Kp. So we're going to go ahead and divide by these two values on this side. And when we do that, we get 20.5 equals natural log Kp. So we go ahead and raise, take B to both sides, and that gives us Kp equals 8 times 10 to the 8th. And this is a really, really large Kp, which, if you remember back to when we were talking about equilibrium laws, that if the Kp is really large, that means that it really favors the product side. of the reaction. So that means that this would be a worth studying as a method for the production of methane, since the Kp lies so far on the product side. And that's it.
19.86. What is the value of equilibrium constant for a reaction for which delta G equals 0? What will happen to the composition of the system if we begin the reaction with pure products? All right, so they're suggesting that our delta G is 0. So if delta G is equal to 0, then R and T are just constants, so we don't have to worry about those. But in order for this to be true, then our Kp has to be 1, because ln of 1 is equal to 0. So ln of 1 equals 0, and for this statement to be true, or for this statement to be true, Kp has to be 1. So ln of 1 is going to be, what I'm trying to say is Kp. Kp is equal to 1. That's what we understand. That's what's understood from that part. So, yeah. And then when we're looking at the Q value, if we're starting off with pure products, then that's suggesting that we don't have any reactants. And so when you divide something out, any number over 0, it actually goes to infinity. So, so Q is equal to infinity, which is really, really big. So Kp is equal to 1, Q is equal to infinity. All right, sweet. And therefore Q is like super, super big compared to Kp. So what does that mean? That means that the equilibrium is going to shift to the reactants. So if whatever pure products we have initially, they're going to decompose into their reactant state, into their initial elements. So, so that's what we understand. So Kp, Q is really big in comparison to Kp, and so the reaction is going to shift to the left in order to reach equilibrium. And that's the problem.
All right, so this is 19.90. It says the standard heat of formation of ethanol vapor is negative 235.3 kilojoules per mole. It says use the data in table 19.3 and the average bond energies for carbon to carbon, carbon to hydrogen, and oxygen to hydrogen bonds to estimate the carbon to oxygen bond energy in this molecule. The structure of the molecule is shown here. So now have the structure. Table 19.3 is where we're getting our values. So it's talking about the heat of formation for ethanol vapor. So the heat of formation is describing the formation of ethanol, which is C2H5OH. And it's getting formed from its elements. So we have carbon.
It just died.
All right, back to number 90. The camera died, so sorry about the delay. But we are talking about heat of formation for our gas here, ethanol vapor. And so we were writing out the equation. So ethanol is made of carbon, hydrogen, and oxygen. So hydrogen gas, oxygen gas, and you have to remember that hydrogen and oxygen are diatomic molecules, and then we have to go ahead and balance it. So we're going to have 2 here, 3 here, and 1/2 on oxygen. Remember that you can have 1/2 coefficients because it just means half of a mole. Now, what we need to do is use our thermochemical equation, or now what we need to do now is find out our separate heats of formation for all of these here. So for them to be vaporized. So we have our carbon here is solid, so it's going to be 2 carbons solid into 2 carbon as a gas is going to be delta H equal to 2 times 716.67 kilojoules, which ends up being 1,433.34 kilojoules. Our hydrogen, we have 3H2, because that's how hydrogen is just normally in the atmosphere. To vaporize that, we need 6 hydrogen atoms by itself. And that is going to give us delta H 6 times 217.89 kilojoules. 6 times that, which gives us 1,307.34 kilojoules. And then we also have 1/2 of oxygen gas vaporizing into just 1 oxygen atoms by themselves, which is going to give us 249.17 kilojoules. So what we need to do here, or what we're doing here, is we're now figuring out the vaporization for the whole thing by itself, which we can do just by adding things up. So what we're trying to figure out here is our actually this equation, but as vapors. So how we have it over here. So it's going to be 2 carbon atoms, vaporized form, plus 6 hydrogens plus 1 oxygen. It's going to give us C2H5OH. And we know that that's going to be the addition of all of these plus that extra, so we don't know the heat of formation for that. So that's what we're trying to figure out. Basically, to get heat vaporization, we're using our bond energies. So we're breaking all the bonds, which is why we're getting them all into separate atoms by themselves, and then we're seeing how much it would take to form all those bonds up again into what we want. So we know that here is going to be the addition of all of these. So that ends up being, it's going to be the addition of all of those plus this. So that's going to be 2,989.85 plus our x is going to be the heat of formation for the whole thing. So the great thing is that we know that the heat of formation for the actual molecule is given to us here, and so we can plug that in over here for it. So negative 235.3 equal to 2,989.85 plus x. And solving for x, we get negative 3,225.2 kilojoules. So this is what it would take to break them all up, since that's what we were looking at. And since we want to know what it would be to put it all together, all we have to do is reverse the sign. So that's the sum of all the bond energies in the molecule, which we got by taking the sum of the energies to break it all up and then flipping it over. Now that we know that the total sum, we can look at the individual bonds now in this molecule, the OH bonds, the CH bonds, and the CC bond. So what we need to do is write an equation for that. So we know that our delta H here, we're going to have 1 carbon-carbon bond, 5 carbon-hydrogen bonds, 1 OH bond, and 1 carbon-oxygen bond. And the carbon-oxygen is what we're trying to guess. We can take the values from this table to plug in here. We know that it was, and then our heat, delta H was this value, so we're going to plug that in. And then this one is, so it's 1 times 348 kilojoules, 5 times 412 kilojoules, 1 times 463 kilojoules, and this is what we're trying to solve for, our CO one. When we add all these up together and subtract them from this side, we end up with our carbon-oxygen bond energy being equal to 354 kilojoules per mole. I know that was kind of a lot, but that's how you do it.